Yeah, thank you very much. So, yeah, first of all, well, thanks for the kind introduction. Thanks to the organizers for having me here. It's really super nice. Actually, I much enjoyed the science discussion yesterday, the talks. Many of the things that I'm going to talk about today link to what we already heard yesterday. So I think that's really nice. It's also fantastic to be in Barcelona. I was never here before for whatever stupid reason, but it's nice. So thanks for having me. And let's see how this works. This is funky. Nice. Okay, so the title of my talk is Jetstream Dynamics Behind Boreal Summer Hot Dry Extremes, Sources of Predictability and Long-Term Climate Risks. So I'm going to present some of the latest research that we've been doing on this topic in my research group. So these type of waves that you see here are really a prime focus of our research. So this shows a snapshot of July 2018. So you see you have a very wavy jet stream pattern all around the globe. And this was associated with heat waves in Western Europe, but also Japan and California, and apparently a flooding event in the Eastern United States. So these waves are important for extremes in summer. They are also quasi-stationary. So they are low frequency waves with a lifetime of about 15 days to maybe up to 30 days. So potentially they might also help in better predictions on S-to-S timescale, seasonal to subseasonal timescales. So basically that's the two topics I want to cover today. So the first part of my talk is really digging deeper into the drivers of these circumglobal wave trains. Please remember this abbreviation. I'm going to use it a lot. Yeah. So the drivers of these type of waves on S-to-S timescales. I'm going to present some insights from climate models, explainable AI and causal discovery algorithms. So I think these new methods that are coming from the data sciences are quite powerful and can really help us to better understand the mechanisms. And then in the second part of my talk, I want to dig deeper into the role of climate change. So how does anthropogenic global warming affect boreal summer circulation? This is not just summer circulation in terms of these type of quasi-stationary waves, but also in terms of the mean westerlies, the mean jet, and the storm tracks. And basically what we see is that over the last 40 years, circulation has weakened. This is something that is also seen in climate models under greenhouse gas forcing. So the question arises, is this weakening of summer circulation, is this becoming attributable? So I will present some new findings there. And if time permits, I will cover the topic of so-called double jet states and the relationships to European heat waves. Good, so yeah, I'm sure you remember. So last summer we've seen many extremes all around the globe, certainly also in Europe. And the heat wave season started very early this year with a record heat wave in Western Europe already in mid-June. So at these very high temperatures exceeding 35 degrees Celsius in areas, in large areas of Spain and southern France. This was related to what is sometimes called the Saharan plume. So this is a strong advection of hot and dry air coming from the Sahara towards Spain, France, and sometimes even the Benelux. And therefore triggers creates these very high temperatures. And if you look at the circulation, so this shows the V wind averaged on 15 days. So this is a 15-day mean, so it's a quasi-stationary component. And you basically see this, this branch of the Saharan plume, right? That poleward flow coming from the Sahara. So that was important for the June heat wave. But you see that this is also part of a much larger structure that basically starts in the Pacific, the American sector, Atlantic, and then over Eurasia. And this was, you know, if you do an FFT on that, it's a wave 7 type phenomena. And yeah, so this was also instrumental in creating a heat wave in the Midwest of the United States. So we had really record temperatures in June in many of these regions. By the way, these are not Celsius, don't be scared. That's Fahrenheit, of course. Anyway, so we had these simultaneous heat waves in the US and also Europe, connected via such a wave train. And that is a more general feature of these type of quasi-stationary circumglobal waves in summer. And Kai Kornhuber has done much more detailed analysis published a couple of years ago. And he's basically showing that wave 5 and wave 7 are important in summer. And the reason is whenever these wave numbers grow in amplitude, they become phase-locked, meaning their longitudinal position becomes locked, right? Always in the same position. That means they can generate persistent weather, and they always tend to do so in the same regions, and that is shown here. So these reddish-colored regions are regions that tend to see hot and dry extremes whenever either wave 5 or wave 7 is in an amplified state. And that is quite important because these regions are also important breadbaskets, particularly, of course, the United States, right? It's a very important breadbasket. Western Europe and also Russia, Ukraine are very important. And what this shows is that whenever these waves are present, we have an enhanced risk of simultaneous heat waves in these important breadbasket regions. In fact, there's a 20-fold increase of simultaneous heat waves. And that can then affect global food production. So you can actually find that signal is actually detectable in the crop data. But so these type of waves are, they present a risk for an agricultural risk. And an example of that was actually 2010. So in this summer, we had a pronounced wave 5 pattern around the northern hemisphere. So this was creating very high temperatures in Russia and Ukraine, but also in the United States and East Asia. So this meant that we had a harvest failure in Russia, Ukraine. Really, the crops were down by 30–40%. And at the same time, we had poor harvest in the United States due to the heat wave there. And that reduction in global production, of course, has its effect on global food prices. That's shown here on the bottom left plot, which show the FAO food price index, which is then spiking following 2010 into 2011. And there has been some research connecting these very high food prices also to the Arab Spring, right? Of course, high food prices on the global markets affect especially importing nations and can drive civil unrest. Good, so it's very important to understand these type of wave phenomena better. So in 2010, we saw these simultaneous heat waves in the US and Russia, but we also had flooding in Pakistan. And this was also related to that quasi-stationary wave pattern. So if you zoom in on Eurasia, so we had kind of a classical omega-shaped blocking over Russia. But this meant, of course, that we have very strong southward flow directly downstream, which meant that we have cold Arctic air going all the way south towards Pakistan. And that is collapsed with the warm and moist air from the monsoon system, and that generated extreme rainfall. So in fact, 20% of Pakistan was flooded, very dramatic, extreme, quite similar to the flooding that we've observed just a couple of weeks ago in Pakistan. Anyway, so we try to understand this particular wave event better, and we did so with this modeling setup at AM3P. So this is an AMIP style modeling experiment. So we force it with constant prescribed SSTs as observed in 2010. And that allows us really to run a very large ensemble, 649 individual runs, such that we have proper statistics and that we can have a look at the tail of the distribution. Good, so before coming to the modeling results, let's first have a look at the Era 5 reanalysis. So this is Z500 centered around, well, for the period last week of July, first week of August, which was really the period when these two extremes occurred. So we see indeed quite pronounced wave pattern, especially over the Eurasian sector. So here on the right, you see that the extremes were also really record-breaking. So this is showing the temperature over Western Russia. So, sorry, this is really difficult. So essentially over this box in Western Russia, the temperatures, and rainfall over this box in Pakistan, so essentially the Indus River Valley. And what you see is that, well, both extremes were record-breaking. The heat over Russia was almost a 4 sigma event, and the rainfall in Pakistan a 3 sigma event, so very extreme. And if we now look at the model, so this is plotting here the ensemble mean for 2010, the anomaly from climatology in terms of Z500. So we see that there is indeed a wave 5 pattern that is present. If you count these highs, you will count roughly 5 going all around the globe. But it's phase shifted, right? It's not really in the correct position as compared to Era 5 reanalysis. Remember, of course, this is a mean over 650 individual runs, right? So that's you wouldn't expect it also. But nevertheless, this wave pattern does increase the probability of high temperatures and also extreme rainfall in Pakistan. You see these PDF shifts to higher values. Certainly for Pakistan, by the way, what's also very important is that we were in a La Nina year. La Ninas amplify the monsoon in this region. So that is also playing a role. But nevertheless, what we can conclude here is that the 2010 SSTs by themselves forced this wave 5 pattern, but it's still phase shifted. And 2010 SSTs were characterized by, on the one hand, La Nina, which you can see here. There. But also very warm temperatures in the tropical Atlantic. So that is interesting, but what I find more interesting, if we now condition on dry soil moisture in June in Russia, which is shown here, so this is showing the 10% driest soil moisture over Western Russia in the ensemble. So we're taking basically 65 runs that have the driest soil moisture in June. And then you see that the circulation pattern is much more similar compared to reanalysis. It's still a factor 2 too weak if you look at the magnitudes. But nevertheless, the pattern is very similar. And again, you're averaging here over still 65 individual states. And this is then really increasing the probability of temperature extremes, but also extreme rainfall event in Pakistan. So of course, it's quite logical that if you remove soil moisture or you're drying the soils in Western Russia, you're going to see more high temperatures over Western Russia, right? Simply soil moisture feedbacks. That is clear, but you also get a remote response. So you get a Rossby wave response that ultimately increases the risks of extreme rainfall in Pakistan. So I think that's very interesting. So it indicates that interactions between wave and soil moisture can have these type of remote effects. Okay, so this is, well, this was an insight from using climate modeling studies. Typically, we actually work with Easy Earth at KNMI. Well, of course, climate models are maybe our prime tool to understand Climate dynamics, they obey the physical laws. We can do these large ensembles now, so that we can really do proper statistics. I personally find nudging experiments also very powerful, where you nudge the atmospheric dynamics and you can try to separate between thermodynamic effects and dynamical effects. So that's very insightful. We also know, of course, that climate models tend to suffer from model biases, right? This yesterday it was already raised, this signal to noise paradox, and that especially on the S2S timescale, it seems that the models are lacking some of the predictive signal, so some of the physics are maybe not well represented. We know that particularly in summer, the models in terms of the mean state, the mean jet state and the mean storm tracks are still quite biased as compared to winter. So that's some limitations of working with climate models. And we have now, since a couple of years, these new data-driven methods at our disposal. And we've been building up quite some experience with applying those to these type of problems, right? So in our research group, we work with explainable AI, shortly mentioned yesterday, and causal discovery algorithms, and also dynamical system analysis. So in this talk, I want to say a little bit more about explainable AI and causal discovery. And yeah, as a general message, I think these methods, these data-driven methods, are quite powerful. Of course, we can directly apply them to observational data. And this way, we can understand from observations things like sources of predictability, causal pathways in the climate system, and also understand the dynamical evolution. So that is great. And I will give some examples. But at the same time, we can also then apply that same analysis to climate model output and really learn better, are these causal pathways actually well represented in the models, or are they maybe too weak, etc. So we can learn a lot more about the processes underlying the model biases. Okay, let me explain you one study where I think explainable AI helped us to understand the system better. And here the aim of this study was to improve temperature forecast in summer over Europe. So we're looking at this Western Europe, Central European region, right? This orange colored region that you see there. And the target here is the probability that the 2-meter temperature exceeds the median, right? The climatological median. And we have a 2-week gap and then a 30-day average for the temperature. So we're really looking at that S2S timescales, where a timescale where the models, the dynamical models, typically have very little skill. And our approach is to train an artificial neural network to apply corrections to the forecast provided by the ECMWF model, right? Point 2 here. So we take the output from the dynamical model, and then we train a neural network to apply a correction. And it's using the input. As input, it uses the ECMWF forecast, but also many observational predictors. Actually, we have about 200 individual predictors that are fed in, but only 3 of them are actually ultimately relevant. And then point 4, then we use explainable AI to understand which of these predictors are relevant and why and when do they apply particular corrections, right? Well, let me first explain you this plot. So this shows actually that this method can actually improve skill. So we have here on the horizontal axis the exceedance quantile. So this shows that for the median, the 0.5 quantile, the corrected forecast, which is indicated here in blue, actually has a higher skill score than the raw forecast. The prior skill score almost doubles for this threshold. So, well, it shows that this approach, applying such corrections, can actually work. Actually, if you go to higher quantiles, then you're running out of enough samples, and therefore it doesn't work anymore. And then in this, so it's great that we get better scale, but then we want to understand why do we get better scale and which predictors are important, and that's shown in that graph here below. So what's shown here on the horizontal axis is more than 2,000 individual forecasts, and for each forecast, and for 3 different predictors, which are, so, sorry, you know what? I'll use this. Yes, this is better. For 3 predictors, which turn out to be the most insightful and the most important predictors to increase scale, we show so-called Shapley values. So Shapley values, well, that's an explainable AI metric, and it gives you information on for each individual forecast, which predictor did what, right? So what we're seeing here is that for these forecasts, this tropical West Pacific SST pattern, so it's kind of a dipole pattern over the warm pool, we see that this dipole was in a positive state and therefore applies a positive correction. So whenever this dipole is positive, it's correcting the temperature forecast in Europe upwards. And similarly, whenever this dipole is in a negative state, it applies a downward correction. So this is interesting, and it suggests that there might be a Taylor connection in summer between the warm pool and European temperatures. And yeah, to understand that a little better, we made here simple composite plots. So on the left, we have a composite whenever the neural network made an upward correction based on that warm pool predictor. And what we see is that it's making an upward correction whenever we have such a pronounced wave pattern present that creates high temperatures over the target region, right? That's quite logical, and has low pressures directly surrounding it. And we're learning that these type of situations predominantly occur during El Nino years or El Nino events. And basically the opposite for the downward correction. So now this wave pattern is shifted a bit further to the east. So the warm anomaly is now over Russia and Ukraine, and the cold anomaly over Western Europe. And this type of correction predominantly occur during La Nina events. So I think this is insightful. Quite classically, we tend to think that ENSO variability is important in winter, less in summer, and certainly less for Eurasia or Europe. But it's likely that there are actually Taylor connection and that ENSO variability and more generally Pacific SST variability is important for Europe in summer. And apparently the model, the ECMWF model, does not capture these Taylor connections well, because the neural network needs to apply a correction. Good. So that's an, I think, insightful analysis from using explainable AI and these type of Shapley values to understand which variables give predictive information. I guess you should always realize that predictive information is not necessarily causal. These links do not have to be causal. So like a simple example, you can have such common driver effects where Z is influencing X and Y. So then X is likely to have predictive information on Y, but still there is no causal link between them. And that's of course a more general problem when you do correlation type analysis, that you're having a lot of spurious correlation, and it's hard to interpret that in a causal way. Spurious correlation can originate from these type of indirect links, common driver effects, and also autocorrelation. So if you have a strong autocorrelation in variable X, then you're going to have a correlation between X and Y, although there's really no causal link between them. So that is a problem with correlation-based analysis. And there have been this this new set of tools, which are normally called causal discovery algorithms, that try to overcome them and learn more about actual causal relationships in a complex system like the climate system. And I don't have the time to really dig deep into how they work, and there's actually different methods out there. But just to give you a bit of a flavor here, what you can do is start working with partial correlations and condition on third variables. So you can regress X on Z and you can regress Y on Z, and then again regress the residuals from these regression analysis. Now, if the regression of the residuals is equal to 0, then you know that X and Y are conditionally independent given Z. Or in other words, the information of Z can explain all of the shared information between X and Y. But if this regression is statistically significantly different from 0, then you know that X and Y are conditionally dependent given Z. So there is some additional shared information, right? So Z might explain some of the shared information, but not all. So that is a useful concept. And then that is, I would say, the essential concept of Trichomite 4.0, which is a Python package developed by the group of Jacob Runge. If you're interested in that, please go to the GitHub website. There's nice tutorials. Anyway, that you have to realize, of course, that we're dealing then with many actors and many lead-lag relationships, and you have to account for all possible spurious correlation between all of these relationships. So what this toolbox does is iteratively loop over all actors and all lags and test whether any of the links is explained by spurious correlation, right? Indirect links, common driver effects, autocorrelation. And if so, you remove that, and then you boil down what starts as a correlation network, you boil it down to a causal effect network. Good, so I think that's very useful. And it creates better interpretable analysis if you do data-driven analysis. So this shows an example of that. This is a study by Sam Vijverberg, and here we were interested in temperature extremes in the eastern United States in summer. So as a first step, he basically does this spatial clustering to find regions that tend to see high temperature events simultaneously. And then he looks more in detail into this eastern US region. So this shows that temperatures in these regions correlate with Z500, so this type of wave pattern. So quite strong wave pattern over the American sector, but also some farther away regions. If you look at SSTs, you see strong correlation with the Indian Ocean, Pacific Ocean, and Atlantic Ocean. And then if you take this causality step, so you remove the spurious correlations, you see that only the Pacific SST patterns remain, so, right? So those we can interpret as the causal drivers of temperature variability in this region, which gets mitigated by such a wave train. And I mean, that also, of course, you know, it links well with our physical understanding. And yeah, so we call this the horseshoe SST pattern over the Pacific, and it can actually give quite good predictability on S2S timescales. But before I get to predictability, first we actually wanted to understand these dynamics better, and in particular the ocean-atmosphere interactions. This was raised yesterday, that in summer the atmosphere can of course force the ocean, the SST patterns, and also the other way around. And climate models might underestimate these type of interactions. So yeah, we try to understand that better, and especially the seasonal evolution of that. So here you see the same patterns in Z500 and SST in winter. And now you see that this very much resembles the classical ENSO atmospheric bridge, right? And that atmospheric bridge leaves an imprint in SSTs in the exotropics. And then we applied this causal analysis to understand whether the atmosphere drives the ocean or the ocean drives the atmosphere. And what we are learning that is on short time scale, so if you use daily data, there's strong two-way feedbacks. So that is quite logical. So the SSTs have an upward, so they drive that wave pattern, and that wave pattern again strengthens the original SST pattern. So you have two-way feedbacks, and that is quite similar. That's happening in winter and also in summer. And these strengths are quite similar to each other. But if we then look at longer time scales, so 10 days and 60-day means, then you see that in winter you have predominantly downward forcing. So the Rossby wave leaves an imprint in terms of SSTs. But in summer, it's the other way around. So it's really the SSTs that drive the Rossby wave. And particularly here, very interesting for predictability, at 60 days lead time, so 60 days ahead, you get a strong connection from that SST pattern to the Rossby wave. So what we see is basically an evolution from, in winter, predominantly downward forcing. So you have the enso-atmospheric bridge that predominantly forces downward and creates this SST pattern. And then in spring and summer, the direction of causality reverses and you get predominantly upward forcing. And this 60-day mean is interesting because that can give you predictability. And this is showing that indeed, if you look at this is the Brier scale score again, some scale metric. And if you then look, if you use this horseshoe SST pattern, you can actually forecast warm anomalies over the eastern US up to 60 days ahead, right? You see that you still have some scale doing better than climatology up to 60-day lead times. So that's nice. It's also very nice, I think, the second point here, that this horseshoe SST pattern projects strongly on PDO, on the Pacific Decadal Oscillation. And this means that strong PDO years have enhanced predictability. So if the PDO is in a very strong positive or a very strong negative state, then you get very high predictability, as you can see here. But if the PDO is more or less neutral, there's essentially no predictability. So this also hints at what sometimes called windows of enhanced predictability. In some situations, the climate system is well predictable, and in others not. Okay, what's fun if you do these type of data-driven forecasts on S2S timescale is that you can quite easily move from a meteorological variable like temperature to an impact variable, in this case, crop data. And we can actually also generate for the eastern US predictability for crop failures in soybean. So we know this region is a very important soybean breadbasket. We also know that soybean is very sensitive to these hot and dry conditions. That is shown in this plot. So we have here on the vertical August root zone soil moisture, and on the horizontal August maximum temperature. And you see all these purple colored dots in the lower right corner. So that these are basically harvest failures, right? So you see if you have the combination of hot and dry conditions, that is most detrimental for soybean. And of course, that's exactly what these type of wave trains generate, these type of hot and dry conditions. So we are actually able to forecast soybean harvest failures and do act from that horseshoe SST pattern. And it's actually better predictable than temperature, which is maybe surprising, maybe not, but from an impact point of view, very interesting. So sometimes including impact variables can actually make life easier. Typically, we tend to think it it creates more complexity. Okay, so now go to the second part of my talk. How much time do I have? So,
10 minutes.
oh, yes, I do. Yeah. Okay, I should be good. I'll be a bit quicker here. Excellent. Okay, so second part of my talk. So how does anthropogenic global warming affect boreal summer circulation? And one of the things that are observed over the reanalysis period is that summer circulation has been weakening. And when I refer to weakening, I mean in terms of the zonal mean westerlies and the zonal mean storm tracks or eddy kinetic energy. So this is simply the westerly flow at, I think, 300 millibar, and eddy kinetic energy, I think this is at 500 millibar, and this is bandpass filtered data. Right? So we take the 2 to 5 days bandpass filtering of U and V. And especially the storm tracks, you see that the reanalysis, over the reanalysis period, we've seen quite pronounced weakening. This is a significant trend. This has been published before. And now in some new work, together with Rai Chemke from the Weizmann Institute, we're looking into, so what do the models really do, right? CMIP, and we're comparing CMIP5 and CMIP6 models. And here in, on the left, you see these brown graphs. That's the CMIP6 models. So you see, it appears quite reasonable what they do in terms of weakening. Certainly under strong greenhouse gas forcing, CMIP6 models have strong Arctic amplification and they show weakening of summer circulation. And this is also something that we reported before for CMIP5 models. But the funny thing is that CMIP5 models seem to be far less sensitive for this type of weakening under greenhouse gas forcing. So here we're comparing trends over the historic period. So you see in black here, that's the actually observed downward trend in the reanalysis. And what you see that the histogram in brown is the CMIP6 model, so they're more or less centered around the actually observed downward trend. And that's quite different compared to CMIP5 models. So CMIP5 models over the historic periods in the multimodal mean have essentially no trend. And also quite strikingly, the reanalysis period are really outside of the CMIP5 model range. And somewhat similar image for U, right? So it's not as clear as for the storm tracks, but again, you see here that the CMIP6 models are more or less centered around the observed downward trend, and CMIP5 models are centered around 0. So in essence, CMIP6 models capture the weakening trend, but CMIP5 models do not. I'll come back to why that is, but let me first say something about the fact that CMIP6 models actually observe these downward trends enable us to do a formal attribution study. And that is shown here. So here we're calculating what's called the fractional attributable risk, which is shown here. So this is widely used in extreme weather attribution. And so you're simply calculating the probability of an event under natural forcing and the probability of an event under natural plus anthropogenic forcing. And yeah, the only difference here is that we now calculate the probability of having a trend with natural forcing and having a probability of a trend with natural plus anthropogenic forcing. And oh, sorry, there's something went wrong here on the x-axis. That's bad. But basically, what this starts at 1995, going all the way to 2020. And this shows the endpoint of the regression, right? So it's regression starting in 1979 till the endpoint. And what you see is that basically over the last 10, 15 years, this fractional attributional risk for the storm tracks weakening is really approaching 1, which really indicates that it's highly unlikely that this would have been possible purely by natural variability. And much more likely that it's actually anthropogenically forced. And we also use some very large ensemble data from the MPI grant ensemble, for example, which is thousands of years of climate simulations to properly estimate natural variability, right? Again, a kind of similar story for you, although it's less pronounced as for the storm tracks. So here you see that the FAR goes to about 0.8 in the last 10 years or so. So it's still much more likely that it's anthropogenically forced, 80%, but it might have been natural for you. Now the question is, of course, why is there such a difference between CMIP5 and CMIP6? And that is really that CMIP5 models underestimate trends in the equator to pole temperature gradient, which is shown here. So here on the horizontal, we have the eddy kinetic energy trends. On the vertical, we have trends in this equator to pole temperature gradient. And these green dots are CMIP5 models. So basically they center around the 0 point. So no change in equator to pole temperature gradient, and therefore also no change in eddy kinetic energy trends. And CMIP5 models are given here with this reddish colored PDF. And they do better compared to the reanalysis. So they do have trend in poleward temperature gradients and therefore also eddy kinetic energy. And this difference, this quite stark difference between CMIP5 and CMIP6 models in summer that has been noted before by this study by Harvey et al. Well, very shortly, it's showing that CMIP6 models are better in representing the climatological state of storm tracks and also Jetstream. The biases are smaller compared to CMIP5. And the forced response, and this is under a future emission scenario, but you see that the forced response is much stronger. It's about a factor 2 stronger in CMIP6 as compared to CMIP5. Both are weakening, but in CMIP6 much more, and that's quite striking. Good, now let me see. Yeah, I gotta move a little bit fast here, but so let's go back to the changes in warming trends in summer over 1979 till present. So here you see era 5 reanalysis, and this is shown as the temperature trend scaled versus the global mean temperature trend. So if a grid point has a value of 1, it has observed the same trend as in the global mean. So you see, of course, that oceans have typically seen a much smaller trend and land areas a much stronger trend. That's what we expect, of course. You see the same thing in CMIP5 multimodal mean. Of course, the contrast between land and ocean is not as stark in the CMIP5 multimodal mean. What I want to highlight here, well, basically 2 things. Arctic warming does penetrate to high latitudes. So at the surface, you hardly see any warming, and you also see that over the Arctic Ocean itself. The Arctic Ocean just acts as a bucket full of sea ice. So all the additional energy is used to melting the sea ice, but not raising temperature. But if you go into higher altitudes, you clearly see warming patterns. That is important. And the second thing I want to highlight is what I call enhanced warming over high latitude land areas. So you see that here, and you also clearly see it in this plot. So very strong warming over Siberia and Canada and these regions. Probably to do with snow ice, snow melt retreat. And yeah, this enhanced warming over these high latitudes might be important for something called double jet. This is a picture from an older paper by Tachibana, which shows such a double jet state. So you have a strong subtropical jet, and you have what's called an Arctic front jet at about 55 north. So that's really following that land-ocean boundary at the Arctic. And of course, when we see this kind of classical general circulation plots, we tend to see subtropical jet and polar jet as clearly separated jets, but those are really highly idealized figures. And normally these jets are intertwined and merged together, right? And it's actually quite well, it's not so usual to see these clearly separated jets even in the zonal mean. But whenever these states happen, they tend to enhance blocking in the mid-latitudes. So this is from a Tachibana paper. So whenever we have a double jet, there's increased probability of blocking. So in this paper, we looked into more detail into that by Evi Russi. So she looked into this, well, this is over the Eurasian sector, and then takes a zonal mean, and then applies self-organizing maps to understand jet states. And she basically identifies 3 different states. So we have this double jet stage, which happens about 1/3 of the time. A single jet state, so you only have really a clear subtropical jet. And what we call here a mixed jet state. And these all occur about 30% of the time, if you like. But this double jet state has been increasing in frequency and persistence in summer. And those states are related to enhanced planetary wave activity over the Eurasian sector. So here we apply again a self-organizing maps, but now on V, right? V to 50 millibar, and only for those days that are in a double jet regime. And what you find is that, well, in this case, you have an amplified climatological wave. So here the contours show the climatological V, or the climatological wave pattern. And the shading shows the anomaly during for this particular SOM. And you see that it's they overlap. So it's really an amplification of the climatological wave, and that favors heat waves in these regions. And likewise, you have kind of a shifted wave pattern, right, away from the climatological wave pattern, and that favors heat waves in those regions. And that's particularly important, apparently, for Europe, and particularly Western Europe. So we know that heat wave trends over Europe have been much more pronounced compared to other mid-latitude regions, as shown here, right? In fact, this is about a factor 3 stronger, the increase in heat waves over Europe compared to other mid-latitude regions. And this analysis shows that this is likely related to that increase in double jet states. And at least for Western Europe, and these regions that are maybe affected by that Saharan plume that I introduced earlier, those regions have seen a much stronger increase in heat waves. And statistically, this can be linked to these double jets increase. So I think this is a very interesting and important discussion. So this shows an earlier paper from my colleague, Geert-Jan van Oldenburg, who very unfortunately passed away last year. And this is his very last paper. And what he's showing here is that the increase in temperature extremes over Western Europe is really outside of the model range. So this is really something we should look into, right? So this is particularly for the build, which is in the Netherlands, where KNMI has its long-running observational station. But you see that the trends are typically far outside of the range estimated by models. And this is still CMIP5 models and also some RCMs. So this is a problem, and I think a very important question for the whole community, and certainly for early career scientists to pick this up. So I do want to wrap up here. Well, this I'm not going to repeat again, but maybe I'll just re-emphasize these 3 takeaway messages. Yeah, so when we talk about summer circulation changes, beware that things are complex. Both the tropics, Arctic, and regional feedbacks, like extratropical SSTs, but also soil moisture feedbacks, are important for boreal summer circulation. I still too often see, people who have been studying the tropics say that the tropics are important. People who study the Arctic say the Arctic is important. We should kind of come together as a community. And I do think, yeah, it's ultimately complex, and many of these things matter Beware of differences between seasons and differences between timescale. If something holds for one season, it doesn't say anything about the other season. And if it matters on short timescale, it doesn't have to, like storm tracks or quasi-stationary waves. It can be very different. And reason for hope to resolve this puzzle is, I think, explainable AI, causal discovery methods, and in general, these new data science methods can help us a lot. Cheers, thanks.
Hi, thanks for a very interesting talk. Now, the system is very complex. We all know this. So, these reasons for hope. Interpretable artificial intelligence. I mean, being so complex, as you say, differences between season, time scales, spatial scales, can we really learn something new from explainable AI? So I would go more in the direction of saying, reason for hopes, we are developing new technologies that allow us to detect much better, we have much better data, and much more computational power. That allows us to do a lot of things. But I'm really very skeptical on what realistic new things can we really discover. I mean, if the signal is there, it should be have seen before. Otherwise, this is a complicated interplay of different things, which gives you this result. It's a black box.
Well, I guess, I mean, I presented that study where we use that explainable AI method to identify that tailor connection that is probably important for European summer weather coming out of the Western Pacific. So I find that a new insight, and at least it triggers you to kind of rethink maybe something you assumed before, like ENSO is not important for Europe in summer. Maybe it is. So I think that is a good trigger where these explainable AI methods can help. Yeah, I mean, having said that, I certainly want to reiterate what was also said yesterday. It's always about getting new knowledge, and that is just, it's an iterative process between where experts need to be able to judge it and understand it. So it's still slow science, right? And not like, okay, we have these tools and we can throw in data and something rolls out. That is certainly not how it will work. I think that is widely agreed upon in the community. But yeah, I mean, I find that insightful. The causality tools, I think they're more insightful than correlation analysis. People have been working with for decades with correlation analysis and making conclusions based on that. And sometimes for the right reasons and sometimes for the wrong reasons. I think causality analysis at least are, a step higher and more insightful. So you're more likely to draw the right conclusions. You can still draw the wrong conclusions, but that's my viewpoint.
Hi, very interesting talk, Dim. Two specific questions. The first one about the recent slowdown of the westerlies in the boreal summer hemisphere. So you've shown that polar amplification may be responsible for the difference between CMIP 5 and CMIP 6, but is it also responsible for the intermodal spread within CMIP 6? And the second question is about the ECMWF failure to capture the tropical Pacific SST influence on summer temperature over Europe. Does the AI also help you to understand why? Is it because the tropical diabatic heating is not well located, or is it because of the mean state and the teleconnection is not well? Do you have any explanation and recommendation for CMWF people to look at that?
Yeah, cheers. Yeah, great questions. Now to start with the last one. I mean, we are looking into that now in more detail. Giem van Straten is doing this work. and he's finishing his PhD right now, and the last chapter will focus on that. Well, what we see, just trying to understand what is this Taylor connection really. There is actually a bit more literature on this already. And it turns out that especially since 2000, this has been an important connection. And before that, not. So it's really a non-stationary type of Taylor connection. Well, the exact mechanism, well, it's quite clear that it's a deep convection in this region, but that it's quite sensitive to where this deep convection exactly happens, right? That ignites Rossby waves. But whether they actually make it all the way towards Europe, I think that's the question, right? And sometimes they do, and sometimes they don't. Because I think that might, for example, be dependent on extratropical SST interactions, right? That I also showed. And that just makes it, I believe, very challenging for a dynamical model like the one in ECMWF, but probably similar for CMIP5 models, to actually capture that all correctly. Right? That is my thinking. I don't have the ultimate evidence yet, but we are looking into it. Yeah. And yeah, the first question about the model spread and Arctic amplification. Yeah, we've done at least one study where we looked into CMIP5 models under strong forcing. So I think RCP 85, end of the century. And then you do see, I mean, there you see that all the models show weakening of eddy kinetic energy and westerlies. And those models with the strongest Arctic amplification show the strongest weakening. So there is this behavior. Haven't done it for CMIP6.
Oh, thanks. Really interesting talk. I think with the sort of circumglobal aspects, these heat wave extremes, something I've never been quite clear on is this perspective of looking at a hemispheric wave number, is that just a sort of convenient metric for identifying these waves, or is there, I mean, is it really some sort of global wave pattern rather than a sort of sectoral wave train? I mean, is it really like an integer wave number rather than sort of some fractional wave number? Or like, how should, what's the sort of way to think about it?
Yeah, I mean, the FFT metric is certainly not ideal, right? It's quite practical, and it works well, or well for some type of analysis. I mean, people have been using different type of metrics. If you do, for example, self-organizing maps on maybe weekly data over V, the V field in boreal summer, you will also find these patterns. And I mean, the danger with FFTs is that you assume it to be hemispheric. But quite often a wave might be regional, right? Only Eurasian or only the American sector. And that will give, you know, it will give a spike in your FFT, but it's not necessarily circumglobal, right? So that's, yeah, the pros and cons. I mean, it was raised yesterday also. I don't think there is an agreed upon consensus about what are the best metrics. But the same is true for like blocking. What metrics should be used and what is good, right? And that's same for these type of waves. So you should always be quite careful, like when you analyze a result or interpret something, what metric was used in the first place. Yeah.
Thank you.
Yeah.
Since we are running out of time, I suggest that now we have the questions from the Zoom participants, and the on-site participants, please ask the questions in the coffee break.
Okay, so we have one question by Dominic Bühler. Thanks for your interesting talk. What do you think is the physical reason that specifically wave number 5 and 7 global wave trains lead to extremes? Did you ever check extreme occurrence during other, maybe lower wave number global wave trains? Because I assume it is kind of expectable that the change for extremes increases the higher the global wave train wave number is, right?
Yeah, I mean, I definitely don't want to say that all the waves are not important. All the waves can also be important. What's interesting about wave 5 and 7, and again, I mean, this is an FFT analysis, so it's it comes with its limitations. But the interesting thing is that in summer, they can persist in the same phase position for extended periods, and therefore, especially for droughts and for these longer heat waves, they are relevant. The reason why they have that type of phase locking behavior, it probably has to do with the land-ocean thermal contrast and also the positions of orography. Rocky Mountains are certainly important, but also mountains over Eastern Eurasia. And that type of thermal forcing and orographic forcing, that seems to favor the phase positions of these waves. So therefore, I think they are important, but certainly all the wave numbers can also be important and cause extremes. I mean, we've done, for example, the larger wave numbers tend to be more important in spring, winter season, when also the jet is stronger.
Okay, so let's thank Dim again for this nice talk.